There we go. So domain and range. So if we want to summarize this or kind of give ourselves a way to visualize this a little bit, think about an ant crawling on this function. It has to stay on the function. But the ant can live forever. It can go anywhere in its universe, right? It could go to the right forever. It can go to the left forever, right? We just want to know what are the x coordinates that that ant can step on. Okay, so could the ant step on an x value of 4?
No.
An x value of 4?
No.
Okay, it could. If it steps on an x value of 4, roughly what's its y value going to be, Jonathan? The ant's walking on this function and it has an x coordinate of 4. What's its y coordinate going to be about? 3. Yeah, it's going to be, not exactly, but we can see it's going to be right there, isn't it? Right? That's going to be a point that has an x coordinate of 4. Y coordinate is going to be close to 3, but a little bit less probably, right? Could it step on an x coordinate of 10? Yeah, it's right there, right? Could it step on a trillion?
No.
Yeah, this ant can live forever, right? The ant could keep walking to the right and eventually get to a trillion. It's going to be at some point where it has an x coordinate of a trillion. Remember that there's nothing to help or to indicate to us that this function is stopping for any reason, right? It just keeps going. We just looked at, we just kind of zoomed in on the map of its universe here, but we could zoom out and see more of its universe if we wanted to, right? If we did, the function would continue off to the right. Could it step on a value of negative 10?
No.
We can't see it on the graph, but what does this graph look like it's doing? As the ant kind of walks off the map here, the part that we're looking at, he's going to continue to go down and to the left, isn't he? Right? And so if we were to zoom out, we ought to see that eventually he could get to a place where x equals negative 10. Now it's going to be way down there, right? We'd have to zoom way out maybe to see it, but it could get there, right? Everybody agree theoretically it could get there? Okay. So what about, could it get to negative a billion?
Yeah.
It could. It's going to be a long ways away, but it could get there. The ant has no limits on how far it can go, though, right? So it could get there. So what do you think? What is the domain then of this thing? It's infinite, right? It's all real numbers. There's no x value that the ant couldn't eventually step on, positive or negative, right? So it's unlimited. And so we say then that it's all real numbers. But we got to know how to write that in a couple different ways. We have to know how to write that using an inequality and using interval notation. Let's actually start with interval notation. It's probably the easiest for this one. Interval notation. Now think what that meant, right? Interval notation, that's where we're going to have either rounded or square brackets. Remember this stuff from last week? And we're going to have two numbers. One's going to be the lower limit and one's going to be the upper limit. So you told me that the domain is unlimited. So what are the numbers going to be? What's the number going to be that goes there or there, if you want to call them numbers? Negative infinity is the bottom limit, which means there isn't one. And positive infinity is the top limit, which means there isn't one, right? And what kinds of symbols do I have to have on the end? I have to have rounded parentheses, because remember the reason that, what do parentheses tell us as opposed to brackets? Like I'm going to skip ahead for just a second. I probably should have started with maybe that example instead. Let's start with that one real quick. Let's go back to the domain and the range. So this one doesn't have an infinite domain. What's the smallest x value the ant could ever have? 3. Okay, so that's the lower limit of its domain, right? Is 3. What's the upper limit? 7, right? The ant can only, its universe is pretty small. It can only walk there, right? Okay, so is 3 included?
Yes.
How do we know?
Because it's a closed dot.
It's a closed dot, so the ant actually can step on x equals 3, right? Can the ant step on x equals 7? What do you think, Maxine? Can it step on x equals 7? Can't. Good. Can't because it's an open dot, right? If it tries to step there, it's going to fall through the hole and who knows where it goes. Some other dimension, I don't know. But so how do we indicate, if we're using interval notation, that 3, it can step on 3? Bracket. Okay? How do we indicate that it can't step on 7? Right? How do we remember that? Takes more ink. Takes more ink to fill in the hole, it takes more ink to draw the bracket, right? What if we wanted to write this using an inequality instead, right? So we're talking about domain, so that's the x variable, right? That's the x variable. So Emily, give that a shot. How could I write that same domain using inequalities instead of intervals? Say it again?
I don't know.
Okay, so describe it to me. Let's just use words. We're picking all the x values from where to where?
From
3 to 7, right? So doesn't that means all the values that are to the right of 3, including 3, and to the left of 7, right? Well, if we're talking about x's, that's the positive direction, that's the negative direction. What's another way in math of saying all the values to the right of 3? X is what? Greater than, right? So we could say x is greater than 3, and actually I could probably say greater than or equal to, because it could be 3. And what's another way in math of saying to the left of 7? Less than. Okay, we see that? And once again, we can see that there's a consistent message being sent here, right? The way that we remember this, our little mnemonic device is, it takes more ink to fill in the dot, it takes more ink to draw the bracket, and it takes more ink to draw the equal sign. Right?
So that whole thing is just the input?
That's just the input, isn't it? Right? Okay, the other way we thought about this too, and I really like this way, and you might actually think this is the best way, is think what would happen if we want to really think about isolating the domain. Sometimes it's easier just to graph the domain on the x-axis. And the way you can think about doing that is taking all of the infinite points on this function, and we're just going to move them vertically down to the x-axis. We're going to squeeze it onto the x-axis. So for example, this point right here, it's going to move down to there. This point right here is going to move down vertically to right there. Right? Now if I do that, would everybody agree, I mean, what's the line segment that we end up drawing on the x-axis starts where and ends where? Where does it start? 3, yeah, right. So there's going to be the starting place, and the ending place is going to be, but what kind of endpoint do I need there? It's got to be open, right? Because that's really not a point that's being included. It's just a boundary, right?
Right.
Everything in between, there's an infinite number of points, but if I squeeze them all onto the x-axis, wouldn't you agree that we're just going to fill that in? Right? So that little line segment right there, that corresponds to what we have up here, doesn't it? Right? It's values greater than or equal to 3 and less than 7. Okay? What about the range? What's the only difference with the range? Walker, how's the range different than the domain? Y values. So it's the vertical part, right? So now we're asking the same questions, or similar questions, but now we just want to know what are the y values that the ant could step on. So what's the lowest y value that the ant could step on here? 6, yeah. And if we scoot these things over to the side, if we drag that one over, that one, if we drag it horizontally now, right? Because if we want to graph the range, we're just going to squeeze the function onto the y-axis. That one would go there, that one's going to go there. No, that guy right there is going to go there, but what's the highest one? What's the highest, vertically speaking, what's the largest value that the ant can step on? It looks like it's right there. Good. So that's going to be at a y value of 10. So it's going to get dragged over to there. And he actually can step there, can't he? Right? So we end up with solid endpoints, and then all the infinite points, the rest of the function, if I drag them over, they're just going to fill in the gap between those endpoints, aren't they? Right, so that's our range. Okay, so Mr. Chichester, help me out here then. How could I write that range using interval notation? What's going to be my lower limit? Now we're thinking vertically, right, this time. So it's almost like tilt your head a little bit, right? So what's the lowest vertical value? 6. Okay, so we got a 6 as our bottom. What's the highest vertical? 10. And what kind of notation do I need there? What kinds of brackets are around it? Yeah, good, because I'm including the endpoints, right? Do I see that? Okay? Jalen, help me out. How am I gonna write that using an inequality instead of intervals? So it's, how am I gonna say that? So we got everything that's bigger than 6, including 6, and smaller than 10, including 10. So what variable do I need?
Why?
Y is, it's a range, right? So I need a y instead of an x. And what do I say? Greater than or equal to 6, there it is, and okay, right? Getting the idea, right? So we remember how interval notation works. We remember what the domain's x, range is y. You can think about this as squeezing the function onto the x-axis or the y-axis, or you can just think about it in terms of the ant. But it all adds up to the same kind of thing. So now let's go back to that first example, see if we can finish this off. So yeah, the domain, it's not limited, right? It goes all the way to negative infinity and all the way to positive infinity. So how would I say that then? If I wanted to write that, it's going to look a little strange, but if I wanted to write this domain with inequalities, what's it going to be? Great, well, but my lower limit is negative infinity. There is no lower limit. So x is great. We're just going to follow the same pattern we did in this first example, right? It's whatever the lower limit is, x is going to be greater than and possibly equal to that if it's a squared off bracket, right? And x is less than the upper limit. It's always that same pattern. Down here, we had a 6 at the bottom and a 10 at the top, and so we got y was greater than or equal to 6 and less than or equal to 10, right? Same pattern every time. So if we follow that pattern here, x is greater than what? Ian, what's that going to be? X is greater than, what's the lower limit, right? All we're saying is whatever shows up on the left is our lower limit every time, right? So it's greater than negative infinity, which is a strange thing to say because that's everything, right? That's all negative numbers, and less than infinity, yeah. So that's how we would write, if we had to use an inequality, that's how we would write all real numbers is an inequality, right? Now what about the range though? Okay, the range is just a little bit trickier here. What do you think? Jocelyn, help me out with the range. So that's the y values. So if I were to squeeze this function onto the y-axis, is there going to be a lower limit? There isn't. You're right. It goes down. Looks like the function goes down forever, doesn't it? Right. So in this direction, we've got an arrow that just goes down forever. Right. Is there going to be an upper limit to this thing? Okay. Now, it probably would help here too. Let me scoot this thing down just a little bit, because I want to remind you about one thing here, right? The range of the function graphed in blue as an inequality is what we're trying to do, but the red line is an asymptote. Anybody remember what that was? We talked about that a little bit. Come on, remember that? What was that? An asymptote. It's like you can never reach it. You can approach it as closely as infinitely closely, but you never get there. And the classic model, I think, is like this one where I walk towards the door. If I cut my distance in half every second, I still never get to the door, ever, right? I just get increasingly closer to the door. That's what's going on with this asymptote. We've got this red line. We'd call this a horizontal asymptote because it's horizontal, right? So the blue graph, this function, as we move to the right, the ant's just getting closer and closer and closer to a y value of 3, but just never getting there, right? Everybody see that? Okay, so back to Jocelyn. So what's my range going to be then, right? So if we squeeze this onto the y-axis, where do I stop the range? I mean, what's the highest y value the ant could get to? The ant can get to, could it have a y value of negative 1 billion, everybody? It could. If we walked far enough to the left and down, it's going to get as low as you want to go. Could it have a y value of 6? Can't, right? Because it's limited, it's running into that asymptote, that's stopping it from going any higher, right? Could it have a y value of 4? Could it have a y value of 2? Yeah, right there it has a y value of 2, doesn't it? Right. Could it have a y value of 2.9? Yeah, I mean, I don't know where, maybe that's like right there, right? Could it have a y value of 2.99? Sure. Maybe right there, right? I probably didn't get it exactly. You get the idea, right? Could it have a y value of 3? See, a lot of people shaking their heads here. That's right. How come? How come? It can't hit that asymptote stopping, right? It never gets to the asymptote. So if I wanted to squeeze this thing onto the y-axis, it's going to go all the way up to 3, but that's where it stops. The question is, what kind of an endpoint do I have there? Open or closed? It's got to be open, doesn't it? Right? Because it never quite gets there. Okay, so how would I write that as a range then? But let's use interval notation. Okay, Jocelyn already told us that there is no bottom limit, right? There's no lower limit to the range. The y values can go down forever. But there is an upper limit, and we decided that was 3. What kind of a bracket or rounded? It's got to be rounded, doesn't it? Because we're not including that endpoint. Okay, make sense? Marissa, how do I write that using an inequality then?
Well, that's the negative infinity.
Okay, so y is greater than negative infinity,
Yeah,
okay? And,
less than 3.
okay, good. Now, I'm going to give you a shortcut on this one. Yeah, you bet. So I'm going to give you a little shortcut on this one, though. This might seem a little strange, but we don't really need to add that infinity, that negative infinity, do we? That's sort of implied, right? The only time we're ever going to add when we're writing an inequality and we use infinities is if it's everything, right? But if we're just taking the values, if we're only limited on the top, if there's only one boundary to the y values, which is at 3, we can make this a lot easier. We can just say y is less than 3, right? If y can be anything less than 3, that includes any number, right? Regardless of how far down it is, okay? So we can make this one a little bit easier. That's all we have to say. Y is less than 3, okay? Let's try one more of these. How about this guy? Domain range. So what do we think on this? Take a second. Ideas? Domain. What can you tell me about the domain? Tanner, what can you tell me about the domain here? Or 2, okay, so you're looking at those numbers as being from right there to right there, aren't you? Okay? So those are numbers that are in the domain. Those are x values the ant could step on, right? Could the ant step on 0? It could actually, couldn't it? Where would that be? So yeah, kind of like right up there somewhere, right? Okay. Could it step on 10? It could. I mean, if we zoomed out, we could see that, right? Could it step on negative 100? Okay, but now, and this is really the things that are hanging people up on this are good to talk about. So what is it that makes you think that maybe it couldn't? Maybe there's an asymptote there or something, right? Possibly. But if there were, it would be drawn. There isn't one. So what's that tell you? It could. There's no limit. There's no limit to how far we can go to the left or the right on this thing, right? So let me go back to you. Then what's the domain? Infinity, right? All real numbers. Okay, so how are we going to say that again? Say it again. Okay, so we can do it that way. So x is, let's start with the x in the middle. X is greater than negative infinity and less than infinity, okay? How would we say it using, Jacob, how would we say that using like interval notation instead? So just the same thing, but we want to use brackets and, yeah.
Oh, I don't know.
Okay, how did we do that before? What was our way of saying, right, that domain went forever, right?
Just waiting for it.
Yeah. Negative infinity to infinity. And that's, think what that's telling you. That's the way in math we say the lower limit is, there is none. The upper limit is, there isn't one, right? There are no limits on it, okay? What about range? Let's look at range here. So is there, you gotta ask yourself now, is there all you're looking for, is there a top or, a lower or an upper limit to the range?
No.
What do you think, Cooper? So range is the y values, right? Is there a biggest or a smallest y value for sure on this thing? -3 is the smallest, isn't it, right? Okay, so that's the lowest the ant could ever go, is at whatever, I guess it's 4 is the x value, but -3 is the y value. Is there an upper limit? No, it could go as high as it wanted to, right? So what's the domain? Y is what? We write it as an inequality. Greater than or equal to -3, right? We only need one boundary, and that's the lower boundary. Y could be greater than or equal to that value. If I squeezed all the values over onto the y-axis, that's going to be the bottom one, isn't it? And then from there, it's just going to go up forever, right? Okay, so how would I write that using inequality notation, or interval notation then? Okay. I gotta have a bracket, right, because I'm including the endpoint. Okay, we're getting this? Would you agree, it's not, there's no writing to do on this stuff. There's no algebra, it's just a matter of kind of applying these concepts, right? Okay, so then we also talked about rates of change, right, average rate of change. And this is really simple stuff, right? All we said about average rate of change, it's a very simple definition. We're talking about over some interval, so we've got a beginning time, it's gonna be a starting place and an ending place. And the average rate of change is just the change in output over the change in input, right? So it's gonna be the change in the y values over the change in the x values. You could think of it for a function, if like x1 is the starting x value and x2 is the ending x value, then it's gonna be the function f of x2, right? The value of the function, for the final x value. We'd call that maybe the final output minus the starting output divided by the final input minus the starting input, right? If we have a graph, it makes it really simple. If we want to know the average rate of change from x equals -8 to x equals +4, well, all we got to do is, where's -8? So there's an x value of -8. So if we go down to our function, that's the point where x is -8 on the graph, isn't it? So it's at -8 and the y value is -5. What about +4? So at +4, there's x equals +4, so we're right there, right? We have an x value of 4, a y value of -7. Okay, so let's calculate the average rate of change. What are we gonna get? So we've got y2 minus y1 over x2 minus x1. What's y2? -7. That's always got to be the second one, right? We're always starting with the first point and ending with the second point, okay? So it's going to be -7. What's the starting y value? -5. What's the final x value? So x2 would be 4. What's x1, starting x value? Okay, and so if we do that calculation, what's -7 minus -5? Minus negative's plus, right? So what's -7, -2. -7 plus 5 would be -2. 4 minus negative, so +8 would be 12, right? So what's that reduced to? Yeah, So there's our average rate of change. And remember, if we have a graph, we can even make it simpler. All we have to do is just draw a slope triangle, right? We're going from there down to there. And the average rate of change is literally the slope of the line connecting those points, right? So we're just gonna go down, we're gonna rise by -2, we're gonna run by +12, and there we get our -2/12, right? No big deal. Okay, last part. So what about one like this? I'm gonna give you at least one problem like this. That looks pretty bad, but I'm gonna allow you to use technology on this. You can use Desmos. You can use Desmos to make this really simple, right? Here's our function. Everybody agree? There's our function. It's telling us, it's predicting a company's yearly profit in millions of dollars, where X is the number of years since 2010, right? So we want to calculate an average rate of change from 2019 to 2023. So what's my starting X value? What's X1 going to be? If X represents the number of years since 2010, that's going to be 9, isn't it? Right? 2019 minus 2010 is 9. So what's X2? What's my final X value? What's it going to be? 13? Okay. So then all I've got to do is if I want to calculate the average rate of change, how much time we got? Oh my goodness. Okay, so then that's all right. That's all right. It's good review. That's fine. You'll be able to do everything on this new assignment, I think, except maybe a couple questions, which we'll get to Wednesday. So then if I want to calculate my final output, isn't that just going to be F, or it's not F, it's P. P of 9 minus, sorry. That's all we're going to do, right? So you can do this in Desmos. I just ran out of time, but you can do this in Desmos. You might remember, I can just put that function in Desmos the way it is, and I could just input 13, right? Start a new line and input 13. It'll tell me what the number is, right? It'll give it to me. I can do the same thing. I can do P of a 9, and I can get the value, the starting value of the function, right?
Is P of X squared in that one, is that just basically like S of X is just a function of X?
This is like F of X, only they called it P for profit. Okay?
I wanted to
All right.
to 10,000. I want to see what. I don't think you will. Like.